The last talk of this session is about epistemic logic for polyglots, and the talk is given by Luis.
So good morning, everybody. My name is Luis. I'm a student of Chris Martens over at Northeastern University in the US, and I'm going to talk about some ongoing work in what I think is a good logical foundation for what I call polyglot programs, which is a type of multi-language programming. And I want to start with an example. So I want to take like 10 seconds to look at this example and for people to guess what will happen. Okay, 10 seconds is up. So it's going to crash. And the reason why it'll crash is because I'm splicing in this string blue value into this shader code, and the shader code's expecting a float. So it's going to scream and say blue is not a float. But the problem with the problem here is that this would type check. This would type check just fine. This is TypeScript. It'll transpile, if that's the word that you want to use. And it'll be like, this all looks okay to me. These are valid strings. It's fine. What's the problem? And it's a problem because like this is an error. This is going to introduce a bug, and we don't want bugs. So this example is not pulled from the air. It's adapted from the MDN, which is a popular resource for people who learn about web development. The real example is actually worse. I have a link to it if anybody's interested. And it involves GLSL, HTML, and untyped JavaScript. It's terrible. So we can surely do better than that. But before I start talking about how to do better than that, I just want to note that this is a common pattern in building complex software systems. I'm going to call these polyglot programs, where you're embedding different languages into a single system. These are arduous to test. You can imagine from writing that code, you write the code, it type checks, it's fine, and then you have to test it. Then you have a runtime error, then you have to fix it, and you go through this cycle over and over again, and that cycle sucks. So again, we can do better than this. And some of you are sitting there screaming in your heads, make a better static type checker. So clearly TypeScript is not good enough. Okay. And if you are thinking that, then I'm glad you're here, because you're thinking about multi-language computation. And this is the study of systems composed of different languages. So like foreign function interfaces, compilers, DSLs, and polyglot programs. And we're all concerned with static and dynamic safety guarantees. I'm clearly concerned about a very simple static guarantee, which is, well-typed programs won't go wrong. So there's plenty of work in this space by plenty of people who are worth mentioning. I see at least one person who works on this type of stuff in the room. There's so many of y'all out there. But the thing is that I noticed is that as far as I know, we haven't really talked about a logical explanation of these types of programs. And I find that very interesting. I come from the sort of tradition of Frank Fenning and folks like that. It's kind of a different style than the folks who talked right before me. But regardless, what we're interested in is this sort of Curry-Howard correspondence and thinking about how to use a logic to give rise to a static type system, calculus for programs, and to understand the essence of some sort of phenomenon. And in particular, I'm interested in taking a natural deduction system and an intuitionistic logic and putting it through the CH pipeline and getting a functional program. So my proposal is to use epistemic modal logic as a way to explain these types of programs. Epistemic logic is a logic about reasoning about agent knowledge. Agents, in this case, we're going to think of them as stand-ins for languages, and epistemic types are going to be for foreign code, or these code in those languages. So before I lose anybody in the rest of the talk, because I'm about to get technical, I just want to share the key ideas here. So first of all, I'm going to introduce the epistemic S4 as a generalization of Fenning-Davies as S4, which is not the same as the classical S4 that we just heard about. Then I'm going to interpret epistemic logic as a calculus for this polyglot programming. And then I'm going to show a small tweak to the calculus where I kind of break my own rule and make something up that goes outside of the logic to get to something that I really want, which is splicing into foreign code. Okay, so the epistemic logic S4. It's pretty small. I mean, so we have our agents, which are just going to be represented by symbols. We have propositions. We have an atomic proposition P, and then we have this box K thing. This box K thing is going to be pronounced box K of A. And it's a lot like Fenning and Davies's box, for those who are in the know about Fenning-Davies's judgmental S4. We have two types of judgments. One is that A is true. One is that K knows A. We're going to have these two contexts that are going to carry things with these two judgments. And K knows A, again, is very similar to this notion of necessity or validity from that Fenning-Davies paper. We aim to prove judgments of the form under epistemic hypotheses gamma and truth hypotheses delta C is true. And I can take that syntax, put it through our Curry-Howard pipeline, and come up with my typing judgments. And the one that I want to highlight, of course, is this K knows A judgment, which I'm going to continue to pronounce K knows A. That's the more exotic judgment here. Everything else is pretty standard. Normally, I would give the rules for epistemic S4, but I don't have time, so I'm just going to give the vibes. So first, knowledge is like validity or necessity from the perspective of an agent, is the way that I want people to think about it. To prove agent knowledge, we need to depend only on that agent's knowledge. So we're going to use the so-called knowledge restriction. And this echoes Fenning-Davies's notion of validity in their introduction rule. And agents can only know true things. And this echoes this hype star rule. And hopefully, when I talk about the polyglot version of this, we'll see echoes of that again. I'll highlight when that comes up. OK. So I just finished talking about Fenning-Davies's S4 and the epistemic S4 and how they're related. And in fact, I argue, well, if you have epistemic S4 with a single agent, it's just Fenning-Davies as S4. So surely we get something with multiple agents. And the main idea is to think of multiple agents as being multiple languages in a system interacting. So we're going to reinterpret epistemic logic as a calculus for glue code. And we're going to think of agents as foreign languages. And the glue code will be the way that they intermediate. So for our types, I'm going to have A denote glue types. I'm going to have a blue tau denote foreign types. And then I'm going to have this A tilde K tau thing, which is pronounced A acts like K's tau, as a type translation. It's a user input, and credit where credit is due. I stole it from Patterson et al. They're colleagues of mine at Northeastern. Thank you so much. I'm staring at the camera. Thank you. So next is our contexts, reinterpreting the knowledge context to now map directly to foreign types. And then the foreign context will be used to type foreign expressions. Then we have another mapping. I'm overloading the tilde, and it's going to be pronounced map gamma to case phi. It kind of has a mechanical flavor to it, and it's defined inductively by these rules. And the one rule that I want to highlight is this one over here, which shows that if I have a target agent and the type is mapped from an agent that's not the target agent, then I'm going to drop that, right? And so that's sort of the knowledge restriction that I was alluding to earlier. We're going to see it being used. We're going to work with two judgments. First is the glue typing, which is the standard judgment that we saw earlier. And then we have our foreign typing rule, which is saying under language K, F will be typed at tau. OK, so our introduction rule requires foreign expressions to type check. First of all, it's this over here. And notice that what I'm doing is I'm embedding the foreign expression directly into my glue code. So it's almost like quoting if you're used to that language. And I'm doing this knowledge restriction that I was talking about here. So I am using only the knowledge. You can think of it logically as I'm using only the knowledge of K to prove statements about K's knowledge. The elimination rule allows us to permanently reuse knowledge. If I have box K of tau, then I can continue on with K knows tau. And then our variable rules are here. So the one on the left is a standard variable rule that you would see from a lambda calculus. And then the one on the right now requires types translation. And it's saying if K knows tau, then we can assume A. And this is to say, if you imagine tau to just be A, then you can think of it as K knows A. Well, like I said, agents can only know true things. So if an agent knows something, then we can assume it's true. And that's what that is. That's what that is. So let's take stock of where we're at. I reintroduced the rules of epistemic logic. I have agents as foreign languages, epistemic language as glue language. Okay, I should be done. So I'm going to rewrite my example here. And just real quick, does this seem right to y'all? Just real quick. Okay. It looks okay, but it's not quite right. It's a valid program. I promise you it type checks, but it's not quite right. And the reason for that is that my original example had parameters for vec4 over here, but there's no splicing going on. And you might think like, well, you didn't use, there's an entire expression you didn't use. Well, letbox won't help us here. And the reason why is that letbox lets us extract from foreign code, but it doesn't let us go the other way around. And I really want to go the other way around. So how are we going to do that? We're going to just tell agents information. Bless you. We're going to just tell agents information. It's a pun on let, I swear. It's just let backwards because it's a let binding. And what it's saying is if A is true and A acts like K is tau, then I can tell agent K about tau. It's almost like I'm telling K something in their language. So we can rewrite our example. If you let me put in a regular let binding in there, this would be our rewritten example in our language, which is great. And here's a 3-language version if you don't like the regular let binding, if you want letbox being used. There it is. And this red language over here introduces 0.8. And then you can imagine some substitutions happening and it ends up there in the yellow language. The thing that I think is cool about this is that you can imagine language B, or the red language, being a little bit more complicated and allowing for user inputs, for example. So a user can like customize their shader code or something like that. For beta principles, this first one comes from a local soundness analysis. So if you've looked at like the judgmental style of doing logic or like Fenning-Davies' work, then they talk about local soundness. I don't have time to get into what that is, but just know that this kind of comes from a local soundness analysis. There's a substitution principle in use being here. But the one thing that I want to point out is that we have to translate from foreign code to glue code here. Next, we have tell. This is a more speculative rule. It doesn't come from any analysis. I had to pull out from the logic to do this. But there's this back translation here. So I think of it as sort of the inverse of what let is doing. But now we can run our example in totality. So we're just going to map floats to floats. There's our example from earlier. Here's type checking. It's hideous. Don't worry too much about it. Just like you can read it as sort of like I'm exporting from the red language, and then I'm injecting into the yellow language. Same thing with the operational rules. It's just a series of substitutions going on. And one thing that's worth pointing out, 2 things that are worth pointing out, is it's kind of hard to see here, but there's this like double translation thing that's happening here with tell, and I just want to be upfront with that, with saying like this is a what's the word? A limitation of tell as it's being used. Remember that tell had a translation going on, and hype star also has a translation going on, and it's hard to see because this is really tiny. But hype star has a translation, and then tell has to do a translation, so I'm double translating, so that seems to be a problem. And then the next problem is, all right, you have a box expression, what do you do with it? I don't know yet, I'm still working on it. Fenning and Davies would say no computation under a box, and that made sense for their staged computation application. So we're still working on what to do here. All right, conclusions and future work. So, we developed the epistemic S4 natural deduction system. We kind of reinterpreted it and gave an analysis of polyglot programming, and then we extended it with the tell expression. And on the horizon, we of course want to think about foreign languages with different properties, parametricity effects, so on and so forth. We want a logical account for tell. One reviewer very helpfully mentioned adjoint logic, and we want to look into that. And last is details on expression translation. One reviewer asked, like, do we even need it? It seems hard, and people don't like thinking about it very much. And we did also question, like, can any of it be automated to make this a usable system for people? And that's it. Yeah, thank you so much.
questions? Please.
I'm a little bit confused about the philosophical setup here, because it seems like there's a bunch of different things that could be called polyglot programming. Like you gave the example in the beginning with like HTML, JavaScript, GLSL code, and then there's like staged programming, and then there's FFI, and these all seem like very different to me. Like for instance, in staged programming, you're generating code that goes into a compiler.
Yes.
And so, but whereas in FFI, like you're calling other code that's been precompiled. And then in the HTML and JavaScript thing, like HTML and JavaScript are like completely different language paradigms. So like HTML doesn't have let bindings.
Mm-hmm.
What in this fairly large space of things that could be called polyglot programming, like which one is your thing?
It would be the last one. I maybe wasn't very clear with that.
Staged programming?
It would be specifically the situation where I'm sort of quoting foreign code in my code base.
Okay.
So I guess that's more similar to stage programming
Okay.
and philosophically, but
So then why is, maybe this is more of an in-depth question, but why is that agents? Because that seems like there's a clear hierarchy of like, there's a host language that generates that generates code, but it's not like they're not on equal playing field the way I would think agents are.
you mean the agents have a hierarchy?
Or just like there's a host language, and then there are target languages.
Yes. Yeah, so the host language, there is a hierarchy. The host language is sort of on a higher plane than
The host
the
language
agents.
isn't an agent.
The host language is not an agent.
Okay.
Yeah. Actually, it's the other way. It's more that agents are on a higher plane than the host language. And the adjoint logic picture for this would actually make it much simpler to think about. So if you want to talk about it more offline, I'd be happy to.
Thanks.
So I think it's time. Yeah. Thanks.